Welcome back to our C++ for parallel applications class. I'm glad you're back, as always. It's nothing worse than for a lecturer standing in front of a class and nobody's in the room. You know, that is kind of embarrassing. So I'm always glad that people show up and that they show interest. That's great. What I want to do today is to continue talking about task-based parallelism. We will touch a bit on concurrency, but it's mostly task-based parallelism, asynchronous parallelism. And without trying to be somehow self-centric or anything, the stuff I'm going to tell you or talk about today is something you will not find anywhere else. So this is really unique work that came out of our group over the last years, and is a very powerful way of writing applications, parallel applications, without hitting the problems that or at least partially mitigating the problems we've been talking about. Especially, we mentioned that Fork-Join Parallelism, as nice as it is, and everybody understands how it works, it is very prone to causing scalability issues in the case when the different iterations take different amount of time. And it's very difficult to properly load balance these fork-join sections of the code. And what I will show you today is a fairly straightforward method how we can mitigate that. Also, you are in for a fairly rough, mind-bending coding experience. So please be prepared for that. And if you struggle with following, really just stop me and then say, okay, say that again. Because I really want you to understand what this is. It allows you to start reasoning about parallelism in a completely different way. Okay, so let's get going. I forgot to enable my McJibble here. Okay, so now it should work. The first two slides are taken from the last lecture, just as an introduction to put you back into the mindset where we stopped last time, where we said that task-based parallel programming, the task-based parallel programming model focuses on distributing tasks concurrently performing different things at the same time, distributing those tasks across a large number of threads or distributing those tasks across different processes. And by the way, starting next week, we will dive into distributed computing. And you will see how nicely that concept of task-based parallelism extends to the distributed case. So we run many different tasks at the same time, either on the same data or on different data, the same computation in each of the tasks or different computations in the task. Everything is possible in that context. The important thing to understand is that task-based programming depends on the knowledge of what are the dependencies between the tasks. Because if you know what the dependencies are, which task depends on what input from what other task, you convey that information to the underlying scheduling system, then you can make sure that tasks that are independent run concurrently and tasks that depend on each other will be scheduled accordingly in a way. And the methods I will present today will show you how you can actually achieve that, to convey that information about dependencies between tasks to the underlying system without having to do anything special, actually. Well, almost nothing special. We will see how that works. Okay, so where are we? Last time we introduced stat-async and stat-future, and I showed you that you can call get on the future and you can call wait on the future, but that's it. So it's really not very useful, and it's one of the major complaints of the community about stat-future, the type stat-future in the standard, that, well, if you want to do really things with it that go beyond just launching a bunch of tasks and then waiting for them in a fork-join fashion, it's almost impossible. That's why standard futures haven't seen the rise and the widespread use that I would like to see in the community. Nevertheless, over the last 15 years or so, the concept of futures, not the standard future itself, but the concept of futures has shown up in many different places, and many implementers of different runtime systems have chosen to use futures as one of the main synchronization primitive. So also the standard has very limited set of higher level parallelization constructs. So essentially you're limited to doing fork-join computing. What I will do today, I will introduce extensions to standard future that we have implemented in HPX, and I will give you some examples how you can use that. And in the end, we will get to some examples where you really will see why these extensions are necessary and what do those extensions enable us to do. So let's sidestep a bit. Let's talk a bit more about HPX in a introductory sense. I have used it here and there on the slides, and we have talked about it in different contexts, but I really want to give you some basic introduction into what HPX is so that you have a better understanding and you can start using it. So HPX itself is a C++ library here developed at LSU for a long time, more than 15 years now. It has grown to a fairly large worldwide open source project. So we have contributors from all over the place, from all over the world. If you're interested in open source computing, parallel computing and open source, HPX is a go-to library to focus on, to contribute to, and to play with. So what HPX does, it gives you a API, a application programming interface that you can use to build applications for shared memory parallelism and for distributed parallelism. And these APIs are very uniform, which has the benefit that you don't have to reason about distributed computing in a different way than when you talk about shared memory parallelism. The good thing is everything HPX has is originally compatible with the C++ standard, fully conforming to the C++ standard. What we have done, we have just added things to the standard. So when you know what's in the C++ standard, you can start using HPX right away, no problem. So it's a set of APIs, and it's a underlying runtime system that helps you scheduling the parallel task in an efficient way. So it will require minimal changes to parallelize your code. We will see today how you can achieve that. And it supports essentially all the programming models we have been talking about so far. So you can do fork-join parallelism, you can do task-based parallelism, you can integrate GPUs, you can do data parallelism. All of that is available there. Just self-promotion, there's a link if you are interested in looking at the source code. It's a medium-sized library, about 500,000 lines of code, of C++ code. So if you're really interested to look into something serious with C++, that's where you might want to start. Okay, so the simplest HPX program, and that's where people usually start, right, is at hello world. So what I've done, it's main, it prints something, it exits, end of story. The important thing to note here is that there is a special header included, which is called HPX main. And that HPX main header makes it so that at the opening brace, a bunch of threads is being launched automatically. And these threads are being joined at the end. So your main already is a parallel program, if you want. And one of those threads, by the way, a random one, actually runs main itself. And that gives you an environment which is parallelized from begin to end. So this header file makes this happen. Main is executed by one of those threads that are being created at startup. And what by default HPX does, it creates one thread per available core and uses that thread. You can think of it as a thread pool in the same way as we discussed that before. And these threads that run on one thread per core, in the end, run all the tasks you schedule and you launch. So you don't have to worry about thread pooling or anything. All you do, you just program against the system, and the parallelization will happen underneath very nicely. Before we start digging into things a bit further, here's the minimal CMake script you will need to build an HPX application. Essentially, the first line and the third line is what you are used to, that you need for CMake. You have to tell CMake what the project is, what the name is, and here you tell CMake, please build one executable that is named hello HPX from that one CPP file. In order to use HPX itself, you have to do two additional things. You have to first tell CMake to find HPX on your system, so you have to have it installed. And then you tell the linker to actually link with HPX in order for your executable to be built. And that's it. So it's very easy to integrate. You don't have to juggle with compiler switches or anything like that. Just build a small CMake script, and that will make it happen. A couple of very simple function calls you can issue in order to investigate the environment HPX is running in. Well, there is the function that is called getNum worker threads, which gives you the amount of threads that are being created at startup. So very similar to if you have ever worked with OpenMP, you have very similar functionalities there, because you can just ask the system, how many threads do I have running? How many cores do I have to schedule my things? Something specific to HPX is you ask it how many localities. And a locality in HPX is essentially a physical process that is connected to your application. So when you start doing distributed computing, you have more than one process that executes your code. And the getNum localities function gives you the amount. So how many nodes do you use, essentially? Please note that if you don't pass the launch policy sync, this function will return a future to you. As many APIs in HPX, instead of being synchronous, they are designed to be asynchronous. But in this case, it's just simpler to invoke the synchronous version, which gives you the number of localities. And last but not least, the last function, getWorkerThreadNum, that gives you the sequence number of which thread is actually running this code at this point in time. Sometimes interesting to know, especially when you have many threads and you want to somehow coordinate between those. Having a means of distinguishing which of the cores I'm running on, this is the way to go. So if I run that, I get, well, on a system that had 8 cores, as I repeatedly said, my laptop has 8 cores available. I ran it on just one process, so it's one locality. And the sequence number of the current thread is, in this case, 4, where that 4 can change. When I run it again, it's completely random which of those threads actually will pick up the main task and will run it. Okay, so do not confuse these two different things. There's getWorkerThreadNum and there's getNum worker threads. One gives you the current sequence number and the other one gives you the number of threads actually running. I have seen people confusing those. I don't know why. It's actually obvious what these functions do. I thought we had appropriate names for them, but people just tend to mix them up. Okay, so how do you set the environment? How do you control how many threads HPX is actually using? Well, there's a command line switch. And by the way, there is any HPX application you can launch with the command line option HPX help --HPX :help. And it will print, I don't know, about 50 predefined command line options HPX, the runtime system, understands. This is one of them. And it tells the system, hey, please launch 6 threads 6 kernel threads when you boot up. So when I run my query environment with that command line option, as you see, the number of threads created is 6. The default for HPX threads is equal all, which will all cores, use all cores. So if you don't specify anything, as I said, it will use all cores. Alternatively, you can set the environment variable, which will then be picked up for the number of threads. All of that has somehow being aligned with the OpenMP parallelization environment, and if you have ever worked with that, you might feel at home directly. So if I run that with 4 threads, well, obviously I get the number of threads 4 now. So there's a bunch of predefined command line options that you can use for your purposes, and you don't have to do anything in order for those to work. They just work magically in the background. All of them start with --HPX:, so they will not conflict with anything, with any command line options you might define for your own application. Okay. So far, so good. That's really just a very rough, high-level introduction to how to use HPX, how to run it, how to make sure that things are set up properly. So let's get to the meat of it. As I said, standard future, as nice as it is conceptually, it's not very useful because you can't really do many things with it. So let's extend it a bit. And what HPX does, as I said, it will implement essentially everything the standard has in terms of parallelism and concurrency, and it will add extensions. So what HPX has is all these types we talked about last time, right? It has a future, it has a promise, it has a package task, it has HPX async. But all those types have been re-implemented to be able to extend them, to add additional functionalities. And in the next couple of slides, I will give you some of those extensions. We'll explain those, and then we will use them in some real-world examples to demonstrate how you can utilize those. So what extensions do we have for a state future? Well, first, you can create a future that is ready to begin with. Might sound trivial, but a very useful facility, and I'll give you some examples for that as well. We have added compositional facilities so that you can combine 2 or more futures and wait for all of them to become ready and then do things. You can sequentially compose them. You can say, okay, here's a future. When that future becomes ready, when the value is available, please run this continuation, run this function automatically once that future becomes ready. So you can chain tasks in a straightforward way. We have a function which is essentially like async, and it's called Dataflow. I will talk about that in a minute, why we need that. There are some specifics about that. Otherwise, whenever you say Dataflow, think async with a twist. We have asynchronous parallel algorithms, and I will use those in the examples in the end. Parallel task regions, I think I will not mention those today, but they're just, I could put ... below, so there are many more things, but I want to focus on the important stuff in the lecture today. So let's start with making a ready future. Making a future that is ready to begin with, that is ready at construction time. So you can directly supply a number or a value, and that value will be provided by the future when somebody calls get on it. So it's very useful in context when you, for instance, have a function that usually requires some asynchronous operation and returns a future, but under certain conditions you already know the answer. So there's no point in jumping through some complicated computation. You just return that ready future because you know what that is. By the way, it also allows you to create a future void. And you might think, what is a future void actually useful for? Why do I want to have a future that doesn't give me a value? Well, you can use it for synchronization. It's really just the event of, yeah, that thing is ready. You can think of a future void as being a facility that is a trigger, right? It's just the notification that certain operations have finished computing without providing a value. Then we have functions that create a future that will become ready after a certain amount of time or at a certain point in time. And here again, you can supply the value that will be provided after 3 seconds or things like that. So let's look at some examples. So I have a function that computes something, returns a future int. It could be our solution to live universe and everything else, or more things. We know that if x is smaller than 0, we always want to return -1. So there's no computation needed. So in order to conform to the API of the function, instead of just returning -1, which wouldn't work, I return a future that is ready to begin with. And it's initialized from -1. If the argument is 0, well, I return 0. And otherwise, I call async and launch some asynchronous task that is doing some more extensive work. And once that task has finished running, async will return or will make the future ready with a result that function has actually produced. Fairly easy to understand, but as we will see, these make ready future functions, as trivial as they might sound, they are very, very useful in certain contexts because you can fill these missing pieces easily. Otherwise, there wouldn't be a way to create a return value for these special argument values if there wasn't some very simple facility like that. If you want to create a ready future after 1 second, so you can create a simple timer function, right? You can say, okay, make this future ready in 3 seconds. And then you can be sure that after 3 seconds, that future will become ready and can trigger some follow-on computation if you want to do it. So in this case, you just pass the amount of time that you want to wait and the value that should be provided after 1 second. And that future will become eventually ready after 1 second, as you might expect. The standard usually has 2 functions when it comes to timing. One is called after, the other one is called until, or at. At means make the future ready at this point in time. So here I just use the current time at 1 second, so it's kind of equivalent to the previous one. But you can specify any point in time in the future to make that value 42 available to whoever is waiting for the future to become ready. As easy as that. So nothing unexpected. Really just facility functions that can help us to compose more complicated code that relies on future synchronization. Let's look at some compositional facilities. First, the sequential composition of futures. And here things get really a bit more interesting. And it's a point where you have to start bending your mind a bit. Because what the HPX future has is a function that is called then. And this function allows you to attach a continuation to a future that will be automatically run when the future becomes ready. So you attach a continuation function that will be invoked when the future becomes ready. The important part, and that's why I colorize that code, is that once the function is being invoked, you know that the future is ready. So when inside that continuation you call .get on the future, that will not block. That future is ready, so it will immediately give you the result. So you are sure that no context switch will happen. And that is very important because it saves us to suspend the current thread, which is always something we want to avoid. The continuation function itself receives the future it was attached to. And here comes a trick. Future.then returns another future which represents the result of the continuation function. And that's where things start getting a bit mind-bending in my experience. So let's have a look at an example. So let's say we have some future to an int that is somehow produced. In this case, I'm calling async, and async launches a simple lambda that does nothing more than returning 1 to 3. Now I create now I want to attach continuation. So I use F1, my future, call .then, and as you see, .then will return another future, which is completely independent of the first one. And the function you can pass to .then is a lambda which receives the original future it was attached to, right? We are attaching it to F1, it's a future int. So the argument is a future int, and it can return whatever it wants. But in this case, it returns a string, so that's why the returned future from that future is returned from then is a future to a string. And what happens here is that at the point when F1 becomes ready, so whenever that async has launched its task and it has returned 1 to 3, this function will be invoked automatically. And that future will hold the 1 to 3. So inside that function, get will not block because, well, it will be invoked only after F1 has become ready, by definition. So we don't have to worry about suspension or by context switching in this environment. The other interesting thing here is, and that is equally important, what we have done is we have told the underlying runtime system, I have two tasks. One task is that lambda, which is doing some work, and I have a second task, which is whatever is in the continuation. But we have told the runtime system, hey, there's a strong dependency between the first task and the second one. So the second one is depending on the first task. So please run the second task only when the first task is done. And without us explicitly saying there's a dependency, we create that dependency between these two futures. So future F2 will become ready only after F1 has become ready, and that is guaranteed. Well, in the end, we just wait for F2, and it will obviously print 1 to 3 as expected. So this is a bit tricky to grasp because, well, we have two futures kind of floating around, one representing one task, the other one representing the other task. But the .then establishes an explicit dependency between those, which is exactly what we want. We want to be able to write code that allows us to convey dependencies between things to the underlying system. And you might say, hey, this is complicated. I have to kind of bend my mind to do that. We will come, in the end, I will introduce you to a facility that actually allows us to turn that back around into normal sequential code, at least code that looks sequentially, which has absolutely the same semantics as this. But I want to show you what the underlying mechanics are, just for you to be able to reason about things. Okay, so what about if you have two futures and we want to wait for both of them to become ready? Well, there is a facility which is called when all. You pass all the futures to an all that you are interested in and waiting, and it gives you yet another future which becomes ready when the two or more futures have become ready. So whenever all of the arguments have become ready, the return future will become ready. There are similar things like when any or when some. When any will make the return future ready when one or more have become ready, and when some do the same thing when at least the given number of futures have become ready. I don't know what happened here. At least there's a typo. I'm sorry for that. Whenever at least the given number of futures are passed, have become ready. I'll fix it afterwards. Okay, let's look at an example again. So let's look at how when all works. We create one future, we create another one. They are completely independent, right? One gives you 1 to 5, the other one gives you a string. And now we say we're interested in waiting for these two tasks, and whenever both tasks have become ready, then I want to do something else. So I call when all with the two futures, and what it returns is yet another one, which is a bit more complicated because it embeds essentially all arguments. It gives you a future to a tuple where the elements of the tuple are the types of the original futures. So in this case, we have a future int and a future string. So that overall future will allow you to access all the results of all the tasks underneath. Otherwise, it's nothing surprising. So when all really makes that return future ready, all F will become ready when F1 and F2 have become ready, and not before that. And then I just, for the sake of it, I attach a continuation to my all future and do some additional work, and then I print the result of whatever that do work gives me back. So you see, we have facilities that allow to orchestrate a execution tree, a dependency tree of futures, where the system will make sure that they are executed in the right order. So we can be sure that this lambda will run only after these two futures, these two tasks have run to completion, which is exactly what we want, right? So the structure of that dependency graph is automatically extracted from the algorithm without you having to explicitly say this thing depends on this thing. But the dependencies are extracted kind of really based on the algorithm you're running. And again, it looks more complicated as sequential code at this point. We will get to the point where you will see that you can write all of that essentially as if it was sequential code in a very simple way. And we will see how that works in a minute. Okay, so async. We know that async passes along all the arguments to the function it invokes on a new thread. But what if part or all of those arguments are futures themselves? When I do an async, have a function, and one or more of the arguments of async are futures. Then what will happen is that the futures are passed through to the function, right? Because all arguments are just passed through, so the futures would be passed through. But that is not what we want, because then if we call get inside the function that is spawned by async, we might run into the issue that get might suspend again, because if the futures I'm passing into async might not be ready yet. So I again have the problem of suspension, which I want to avoid. So that's why we created a facility which we call Dataflow, very similar to async from its API. But the return future, the function will be only if one or more arguments are futures, the invocation of the function will be delayed until all the futures have become ready. So you can be sure that inside that function that is passed to Dataflow, all arguments that are futures are ready. So you can call get on them without having to be afraid that the futures might suspend. They will not, because by definition they are ready. And a Dataflow again returns a future, same as async, which becomes ready whenever f has finished running. And that future will hold the result of whatever f has returned. By the way, non-future arguments are passed through in the same way as done for async. So nothing to worry about there. So you can think of Dataflow as semantically being equivalent to doing when all with a bunch of futures and then attaching a continuation, which is our function f. It's just a simpler way of expressing that. An example, well, I create two futures again, our friends, we have seen those. And then I call Dataflow, passing in the two futures and a lambda, which receives its arguments, future 1, future 2, which are essentially these two. But the lambda will be invoked only once these two have become ready, which guarantees that this get and this get will not suspend. Again, is exactly what we want. And as said, the return future represents the result of do work. So whenever do work finished running, the overall return future becomes ready, so you can print the result in the end. So you can think of Dataflow as a more sophisticated way of combination of parallel and sequential composition, because it does both, right? It waits for the two things to become ready and then sequentially attaches this continuation to both of them, so you can do your computation and chain things in in a task-based way. Does it make sense so far? Yeah, good. Okay, let's go back to parallel algorithms. We talked about those. I said that C++ has these parallel algorithms, the C++ standard since 2017 now. That's just some of those. We have looked at some of those algorithms. And the way you create parallelization and the way you parallelize those algorithms based on the standard is that you pass an additional first argument to those arguments, to those algorithms that in the simplest case is execution par, which instructs the implementation, hey, feel free to parallelize that invocation of that algorithm. So if we look at simple example, if you want to fill a range between begin and end with zeros in parallel, because the range is very, very large, we pass that execution par as a first argument, and fill will run in parallel, and we'll try to optimize the execution of that. Now, what is this? This is a time graph. On the x-axis is time. On the y-axis, you see thread numbers. So each of those lines represents the utilization of a particular core. So thread 24 is utilized whenever you see these green, the highlighted regions. And this is exactly what you see when you have a parallel algorithm and invoke it repeatedly on a system with a bunch of threads. In other words, the green regions means the parallel algorithm actually does work. And the white region is that synchronization between invocations of that parallel algorithms. So you have what a situation we want to avoid by all means, because as we discussed when we talked about Amdahl's law, any sequential piece of execution hurts our scalability. And essentially these white gaps in between the utilization and our cores means that there is some of the threads is actually sequentially executing some code in between the invocations of the parallel loops. And this is a classic way you see in many classic parallel applications, be it shared memory or distributed, that you have these bursts of CPU activity. And then you have these gaps in between the CPU activity where nothing can be done because the whole system waits for one thread to do synchronization, to do I/O, to set up the next loop or things like that. So this is exactly what limits our scalability, why we can't get 64 times speed up if you run something on 64 cores. This is what's happening in systems today. And what I want to show you is how we can actually overcome that. And that might be interesting for you because, well, we want to optimize things, right? So let's see what we can do in terms of programming model in order to overcome this kind of intrinsic problem of fork-join parallelism, because that is what fork-join parallelism gives you. It gives you these regions of fully parallelized code followed by a region where nothing is happening because only one thread is either synchronizing things or setting up the next loop or doing I/O or things like that. Just imagine you were able to squeeze that. You would probably run only half of it. You would be twice as fast compared to what we achieve here. And as we will see, you can actually do that. I hope to be able to show you that graph today. Okay, so let's go back to HPX and talk about what we have done in HPX to parallel algorithms, except just implementing them as a standard provides it. So you might, as you already might have guessed, we have a fill algorithm, which is the same as standard fill, and you can pass the execution policy. Please note it's the HPX execution policy here. And it will run things in the same way as the standard algorithm would do. But as I already mentioned, sometimes you want to have more control over it. You don't want just to tell the system, hey, run this in parallel. Sometimes you want to limit things. You want to say, run this in parallel, but use 4 cores only. Or run this in parallel, but run it over there on this node. Or run this in parallel and define certain affinities. Remember that num block magic variable I was using when I showed you how these parallel algorithms might be implemented? How many partitions do we create? Do we create as many partitions as we have cores? Do we create only 3 partitions or 28? And that are things you might want for the user to control. You might want to give the user the ability to fine control how parallelization is happening. And the way we do that in HPX is by introducing a concept which we call executor. And we might talk about executors on a later lecture a bit more. But for now, just think about an executor, a object, a type that controls how, where, and when things are being executed. So you can tell it, run it on these 2 cores, run it on that NUMA domain, run it on this locality. And then you attach that executor to your parallel execution policy with a special function which we call .on, and that will make the fill algorithm obey and use that executor to schedule things. So if you have a special executor that limits things to 2 cores and attach it to par, then fill will run on 2 cores. So you have a means of controlling these things in a more fine-grained way. And there is another option. You can use .with and pass additional parameters here, like the number of blocks or the size of the partitions, things like that. But the idea is the same. You have means of controlling how the parallelization is actually happening, where the parallelization is happening, and what resources to use for that. But the most important thing HPX adds, besides being able to extend the parameterization of the execution policies, is it introduces new execution policies beyond par and sec, namely a par task and par sec execution policy, which allows you to turn the synchronous invocation of a parallel algorithm into an asynchronous invocation of that algorithm. So instead of waiting for the algorithm to return until it's done, it will return right away, give you a future, and the future becomes ready when the algorithm is finished running. So in all cases, a formally synchronous function returns a future t, where t is what the synchronous version of the algorithm would return in the first place. So it instructs the parallel construct to be executed asynchronously. It kicks off the execution, runs the parallel algorithm in the background on the side, while you can do other things in your program. And it allows the integration with all the asynchronous control flow constructs we talked before. You can attach a continuation, you can combine it with other futures, and so on and so on. So it turns these parallel algorithms into the building blocks of task-based parallelism and treats the whole parallel algorithms as one task and allows you to coordinate with other tasks in the common way. But the main benefit of this is that it allows you to mitigate the bad effects of Fork-Join parallelism. I showed you the graph, these gaps. Now imagine you have a parallel algorithm, you run it asynchronously. And when the parallel algorithm runs full speed and has enough work for all cores, things are fine. But towards the end of the iterations, the parallel algorithm starts petering off. It starts tapering off because cores start being ready with their piece of work, which is exactly what we want to avoid. In the very end, you have only one thread which waits for all of them to finish. So if you run things in an asynchronous way, you kick it off, then you can do other things concurrently to the parallel algorithm, which will be utilizing the cores as they are being freed up by the parallel algorithm work, right? When things are petering off, cores become available, and those cores start running other tasks that you might schedule independently of the parallel algorithm. So you start utilizing the gaps in utilization you had before because you do fork join. You start utilizing those for your benefit, and that will speed up the overall computation significantly. So that is essentially the trick you will apply. Any questions so far? Okay. Let's have a look at some examples, and I want to show you at least 2 examples, if time permits, a third one. The first 2 examples, one will be about how you can parallelize with task-based systems a iterative algorithm, and one where we'll implement Quicksort in parallel, just with a couple lines of code, but fully parallelized as well. Okay, let's look at a problem. Let's say we have a sequence of elements, and some of those elements are marked up somehow. Just imagine you have an email client, and you say this email, this email, this email, this email, and that email. So you mark them up arbitrarily. Then you grab those things, those emails, and drag them into a different position. You want to get them here. So in the end, you want to have the sequence, right? You want to kind of collect all the emails, and you want to drop them in that one spot where they are bunched together. How would you implement that if I asked you to do that? Anybody? What would you do?
Like sequentially?
Well, just sequentially, yes.
I guess iterate the array and then pick the one that you want to select it and take it out and then...
So you would create a separate array and copy things over, and then you copy things back. Okay, would work. Horrible solution, but okay, would work.
You take a future and then when all are there, then you can put them back.
Well, can you do it without putting them back? Without storing them somewhere? Without additional memory? Just in... Well, I wouldn't ask that question if you wouldn't be able to do it, right? So let me give you a hint. Look at this one problem as being 2 problems. Just divide it wherever the insertion point is. And now you see that you actually have just to reorder the things in both parts in different ways. In the upper part, you have to reorder them in a way that the marked up come last. And in the lower part, you have to reorder them that the marked one come first. Right? You just reorder them. And luckily for us, there is an algorithm in the standard library which is called partition. And that algorithm does exactly that. You give it a predicate. The predicate returns true or false. It returns true when the thing is marked, returns false if it's not marked. And partition will reorder the elements in a way so that first the marked ones and then the unmarked ones will come out of it without additional memory. It's just doing switching, moving things around. So if we assume that we have 3 iterators, the begin iterator, the end iterator, and our insertion point, I call them B, L, begin, last, and P. And what we want to get out of it is we want to write an algorithm which returns us a pair of iterators that show us where the insertion region is, so that we can do other things afterwards, right? We want to run that algorithm we want to develop, and we want to get the insertion region out of it because we want to send those emails, for instance, right? We want to iterate over those emails only afterwards, or do other things, or delete them.
Not divide at the end because that 2 are already together. So
yeah, well, yeah, sure, you don't. Yeah, these 2 are together already, yeah, sure. Think about it, you have 3 million elements, right? So you don't want to look at each of the pairs separately or things like that. So partition is doing that very nicely. So let's look at the sequential execution, right? Or how to write that sequentially. I call the function gather. I'm passing in these 3 iterators, F, L, begin, end, and the insertion point, and the predicate, which decides whether an element is marked or not. I call partition on the first half from F to P, but I have to negate the partition, the predicate, because, well, partition moves the marked up ones first and then the not marked ones. That's why we negate it. Then we do the same thing for the other half from P to L, this time with a straight predicate. And the interesting thing is that stable partition returns the partition point. So it returns this point for the first section and this point for the second section, exactly what we want. It gives us the 2 iterators. So all we have to do, we just return those iterators as a pair. Done. Fine. Just because we haven't talked about partition, there are 2 versions of partition. std partition and stable partition, which reorder the elements in a range such that all elements for which the predicate returns true precede the ones for which the predicate returns false. And it has O(n) complexity, which is nice. It goes over the sequence once and reorders things while it's doing that. For stable partition, the relative order of elements is preserved. For non-stable partition, the order of elements with the same result from the predicate might not be preserved. Same as with sort and stable sort. Essentially, it just maintains the order or not. So stable partition is a bit more, requires a bit more computation than partition, but yeah. Let's use stable partition in this case because we don't want to change the order of our emails in our list. And it returns the iterator to the first element of the second group. It's kind of the partition point. Now, how do we parallelize that? How would you do that? What would you do to parallelize this? I gave you all the information you need. Well, in the simplest case, pass std execution par to the stable partition, and you get at least two parallel regions, one for the first half and one for the second half. Always assuming this overall sequence is long enough that parallelization is actually worth doing. Otherwise, this certainly doesn't make sense. But let's assume we have 1 million elements. We want to do that. OK, so let's go even further and say I want to make it asynchronous. I want not only parallelize it, but I want to create a version which I can kick off, which gives me a future whenever it's done running. And as before, the future will return exactly what the sequential algorithm was returning before. So it's a future to a pair of two iterators. The arguments are the same, right? Nothing will change there. And what if we used stable partition and were passing in the parallel task execution policy, which runs this one in asynchronously and runs this one asynchronously, and both give us a future back? That immediately tells us that, well, these two run in parallel. Each of them is parallelized, but they run concurrently at the same time. Because the first stable partition returns right away once it has kicked off the computation. And then we immediately kick off the second stable partition, which allows us to even better utilize the machine because we have even more tasks in flight. Right? When one of them is tapering off, the other one can start running and can utilize a machine. It doesn't have to wait for the first one to finish, and then we kick off the second one. But now we have a problem. We want to return a future to a pair of iterators, whereas we have only two futures to one of the iterators each, which is kind of weird. But we have to do some mind bending. And if we use Dataflow for that, we get exactly what we want. So we pass these two futures in, f1, f2. And remember, Dataflow invokes its function only once these futures have become ready. So at this point, when the function is being invoked, we know that both partition steps have finished running. We get the two futures in, we passed in. Well, and all we have to get is the two iterators out of those two futures. Call make pair, which should be std make pair here, I'm sorry. And that's it. Then this function will return a pair, which Dataflow will turn into a future to a pair because Dataflow returns a future to whatever the function returns. And that's exactly what we need. So as you can see, the importance of doing asynchronous computing, because now we can run these two fully parallelized partition steps at the same time if compute resources are available. So when one of them is shorter than the other, when it's tapering off, it can already start with a second one to do the computation and fill our computational resources much, much better. Now, let's step back for a second. What have we been doing? What we have done is we have created a dependency tree of 3 futures. The one that is returned from gather async depends on the other ones. So there is an execution tree, a dependency tree, which is implicitly created. And that dependency tree can be used by the runtime system to make sure that this function is run only once these have become ready. And that is a very important concept. Now you might say, I don't understand that. I don't want to write this code. This is way too complicated. Why do I have to pull my brain out, turn it around, inside out, and plug it back in order to understand what's happening here? Because that is exactly what's happening, right? You somehow turn things around into a event-driven way of thinking about things, which is not very easy. Now, you're lucky, you got lucky, because in C++17, the C++ standard has added a keyword. That keyword is co-await. Strangely named. Don't ask me why they called it that way. Co_await. And what you can do, you can utilize the facility of co-await to achieve exactly what we want without having to rip our brain out and pulling it inside out. So I have these two things. They are the same as before. But now instead of using Dataflow, I'm using co-await. I'm saying co-await 1. It's again the std make pair, not HPX make pair. I apologize. So co-await f1, co-await f2, create the pair of whatever these things return, and return the result to the caller. This code is 100% equivalent to the Dataflow-based code, but is a sequential code, right? It's how you used to think about things. You do one thing, you do another thing, and whenever you need the result of a future, you flap a co-await in front of it. And it will give you the result. But it will not wait for F1, it will not suspend, but it will instruct the compiler to restructure this function internally in a way that everything that comes after the co-await will be attached as a continuation to the thing you're waiting on. So you get exactly the same thing as we were doing explicitly with a Dataflow or with a .then. Essentially, you can think of that as .then, which runs this one, .then, which runs this one, and the overall result gives you what you need. But it's nice because it is normal syntax. People can reason about that. If you compare this to your original sequential code, you will see that there's almost no difference. The only difference is that now you run these two partitions as asynchronous tasks, and that you slap the co-await in front of the futures, and you're done with it. Okay? And this is the syntax I will use from now on. All the other examples I will show you. So whenever you see co-await, think of it as magic which attaches whatever comes after as a continuation to the thing you're waiting on, automatically. The compiler does that for us. We don't have to do that in our heads. We can reason about it in a very sequential way, which is just great. Okay, now let's apply that to some recursive algorithm. And I want to use Quicksort. Why Quicksort? Everybody knows Quicksort. It fits on a single slide. It does something useful. So let's do Quicksort. Let's start with some sequential implementation of Quicksort. I'm doing the actual operation only if size is larger than 1. So if I have more than one element in my input sequence. If I have more than one element in my input sequence, I'm using partition again. But this time, I'm partitioning based on whether the current value is larger than a selected pivot point or smaller. Right? You might remember Quicksort selects an arbitrary value in our sequence, and then it orders them that everything that is smaller than that value goes first, and everything that is larger comes last, and then it calls Quicksort recursively on the subsequences. This is what Quicksort is doing. So very simple, and again, just by using partition, you don't have to do any work. It's the same thing. For now, I just selected a very primitive algorithm to select the pivot, which I'm just using the middle point of our sequence. But you can use some more complicated selection of the pivot if you want to. And the predicate then checks whether that pivot point is, the current value is actually smaller than the pivot point or not, and the partitioning will reorder things in the way we want. And then we call it recursively from first to pivot, because pivot is whatever the partition returns, it gives you the partition point, which is exactly our division between we want to sort separately, and then recurse into it. Should be kind of familiar to everybody. Everybody has seen Quicksort. Okay, how do we parallelize that thing? How would you do it? What would you do to parallelize that in a straightforward way? No idea? What if we just pass did execution par to our partition? Parallelizing the partitioning of the thing, and then calling recursively into partitioning the subsequences. Sure, exactly what we want to do. So we pass par to partition, get our partition point back, otherwise the same thing. The only thing I have added is that I'm parallelizing only when a certain number of elements is available. So if I have less elements than the threshold, I'm just switching to the sequential sort algorithm. Because, well, what's the point in partitioning down to single elements? You just usually stop the quicksort when you have, I don't know, certain threshold of elements, and only then it's worth doing parallelization. Because if you have less than the threshold, which you would have to figure out for yourself, but if you have less elements, then parallelization wouldn't give you anything. So that's why that additional thing. And then I do the recursion as before. Great, we parallelize things. But the problem here is that this code will give you exactly the utilization scheme I showed in that graph in the beginning. It will do parallelization, well, nothing. Parallelization, nothing. Parallelization, nothing. So you have exactly that effect that we want to avoid. It will probably run faster than the sequential version, but it will not give you the full speed you might achieve by the system. So what can we do? Well, what if instead of returning nothing, we just return a future and turn that quicksort into a sequential algorithm? Let's do it in the same way as before. If its threshold is more elements than the threshold, we will do parallelization. Otherwise, we will do sorting sequentially. And once we are done, we just return a future which is ready to begin with, right? That one returns a future void which is ready to begin with. Because when we fall into the sequential case, we are done. There's nothing we have to wait for. So now let's look at the parallelization. Well, again, instead of running it in parallel, we run it in parallel and asynchronously, which makes partition now return a future which will be ready whenever the partition has finished running. But now we have a problem because we can't just use the pivot directly to call things recursively, because that pivot might not be available, right? It's a future. So we have to wait for that pivot to be done. So we attach a continuation to our future, which then calls quicksort recursively. And whatever quicksort returns, because quicksort now returns futures, remember, right? We return a future. So we have to use when all to wait for both parts to finish before we can continue. Again, works nicely. But again, it's code you don't want to write. You really don't want to write because it's way too complicated. You get it wrong. You know, it's difficult to reason about. So let's do that same thing with our nice co-await facility. Well, we just slap the co-await in front of the partition, and now we get the iterator directly. We don't get the future. We get whatever that thing returns. And then we can do a when all and co-await on whatever the when all returned. Much easier to reason about, much easier to write. And if you think about it, it's almost the same as the sequential version of our algorithm, which is again what the benefit of this. You are able to write a sequential version and apply a certain set of very well-defined transformations. You don't even have to think about those transformations because they are very formal, and you get a fully parallelized version of the code. So what did we get? This is a graph I showed you before. What do you think we will see from that last version of the algorithm? Well, again, I wouldn't show you if I wouldn't be able to brag, right? So this is what you see afterwards, once you run the other algorithm. You see that these gaps in utilization we were seeing before are completely gone, or almost completely gone. Because as soon as one of those parallel regions, parallel partitions, has finished running, other things that already scheduled, because Quicksort returns essentially immediately. It runs through all the code and gives you a future back on the upper level immediately. And then you wait for that future, and the whole thing will run and will do its thing. And while it's doing its thing, it will nicely utilize all the compute resources we have. And this is what we want. That is how we can beat Amdahl's law when it comes to fork-join parallelism, by launching algorithms for join regions asynchronously and make sure that there's always more work available than I have cores. Because as long as I have more work scheduled to be done, the runtime system can schedule and can run that work whenever some resources become available. That is exactly what HPX is doing. So you feed it with 1 million of tasks and say, go ahead, do it. And it will go through those millions tasks in the right order with the right dependencies and will give you the result eventually in much shorter time compared to the original code. This is what I meant. You don't see that anywhere, because I haven't seen that anywhere. People doing these transformations and still providing an API that you can actually use as a mere model. You don't have to rip your brain out and come up with completely way of thinking about programming. No, it's still sequential execution of things, just with some additional twists that are very formal. And once you understand what these transformations are, you can apply them yourself without much training and without much experience. We called that technique, well, it's probably not very inventive, but we called it futurization. It's a technique that allows to almost automatically transform code that delays the direct execution of things in order to avoid synchronization and suspension. It turns straight sequential code into futurized code, and the idea here is that the code is no longer actually performing the computation. But if you think about our Quicksort, the actual function is not doing anything. All it does, it sets up a dependency tree of futures and gives you the root of that dependency tree, returns that back to you. That's all what Quicksort does. So Quicksort itself doesn't do anything anymore, but it composes that tree that in structure is equivalent to the algorithm you were running. So once the tree is then executed, it produces the same result as before, but without any suspension in between, which is exactly one of the benefits. The other benefit is the possibility of overlapping the tapering of the fork-join regions, which normally kills performance in a very bad way. So the execution of that tree, the unraveling of that tree, is performed with maximum speed because the dependencies between the tasks are hard-coded in that dependency tree. And that is a trick. So in the end, you can think of it that you get an emergent property of auto-parallelizing your code in a certain way. It's an amazing thing. We have done a lot of experimentations with that, and we have always seen excellent performance results from it. So if you really want to play with things and really want to kind of understand that, I'd suggest that you grab HPX, start playing with it. It will just work without you having to break your neck while doing so. Any questions about that? No? Okay. Well, I have another example, but that won't take more than 10 minutes, so that's why I will not show that to you today. I will add it to one of the lectures in the future, because it's a distributed example anyway, so it fits better into next week's or the week after. But for now, just the take-home is asynchronous computing is where you get performance in parallel when you have real parallelization needs. So always try to apply that for your applications. And if you want to use that for your project, go ahead, do it. And do 2 versions. or three: sequential one, the parallel one, normal with normal fork join, data parallelism, and the asynchronous one. And look what you can get in terms of speed up, if it really is worth doing. Okay? Okay, that's it. I'll let you go for today. Thanks for your attention.